Welcome back to a new video. In this video we will discuss the MOSFET amplifier frequency response, and we will use the short circuit time constant method to determine the lower cutoff frequency and also the voltage gain for this specific circuit. We will discuss everything step by step in our calculations and verify these in SPICE simulations. Alright, we have the following circuit. You see here the MOSFET M1. The specification for that MOSFET is shown here. We have the threshold voltage 2 volts, the Kn, the process parameter is 5 milliamps per square volts, and the lambda is 0, so that means we don't have the channel length modulation. We also have the resistors and the power supply here, VDD, and the capacitors in this circuit, and these three capacitors will determine, we will see that shortly, the lower cutoff frequency for this circuit. The values of the resistors and the power supply, VDD, and the capacitors are shown here. So what we want is, we would like to determine the maximum voltage gain and also the lower cutoff frequency after that. Okay, we start first with the DC analysis as shown here. So what we do, we always assume in the beginning that our circuit is operating in the saturation region. That means the drain current will be then defined by a quadratic equation we will see shortly. Now, in order to fulfill the saturation region in the MOSFET circuit, we need to fulfill two conditions. One of them is the VGS, which is the gate to source voltage must be at least the threshold. So it means above or exactly 2 volts. And VDS must be then the VGS minus V threshold. That's actually what we need here at the minimum. Okay, the DC circuit for our DC analysis means the following. You have an open circuit for the C1 and also the C2, because for DC these two capacitors are open, so you don't have the RI anymore, and also the load is gone, and the CS is also open, so you only have this mid part of the circuit, which is actually shown here. We also labeled here the currents, the IG, the drain current and the source current. Since the gate current in the DC is 0, that means the source and the drain currents are equal to each other, so the gate current is 0. Okay, I already labeled here the gate node, so that will be used later. In this case, we can determine the gate voltage by using the voltage divider rule. Why? Because the current flowing in the gate is here 0. That cannot be done if you have the BJT here, because there will be some current, even though it is small, but it's not 0. So we need to then use a Thevenin, for example, for that. In this case, we can use simply the voltage divider rule, so we can say R2 over R1 plus R2 times the VDD. And if you now substitute here the values, the 500 kilo ohm and the other 600 kilo ohm here, and also the 18 volts for our VDD, you get here 8.182 volts. Now we can now apply the Kirchhoff's voltage law, looking from the node G all the way to ground. So we can say VG is equal to VGS plus the voltage across the RS, that's shown here. And I see here the IS, which is the source current, which is also equal to the drain current, ID. Now, since we assume that the saturation region is valid, we can have the following drain current formula we can use, that's given here, as said before, as a quadratic equation. You see the Kn appearing from the MOSFET specification and also the threshold. So we can substitute this as it is a source current, because those are the same. So we take them together and we have this expression, and you see here in this expression only one is known, because the VG is known, the RS is known, and also the Kn is known. So we also the threshold voltage is known, so we can solve this. So the left side is 8.182 volts, and we also have the 630 ohms, and also the process parameter Kn, and also the threshold. So we can just solve this, and you can now do it by calculator or by hand, doesn't matter. Then you get the two solutions. One of them is 0.4314 and the other one is 3.251. Which one is now valid for this circuit? Now we have said that our saturation region is valid. That means the gate to source is at least the threshold. If I look at this one, this is less than the threshold voltage, which is then not valid. And this is larger than threshold voltage, so this is valid. So we have two solutions, of course, mathematically, but this is the one which will be valid for this circuit, which means the VGS is 3.251 volts. Now, since we know that, we can use the formula here for the drain current in order to calculate the drain current here. So just substitute here the value for Kn given here in the example and also the VGS we just calculated, and you get here 7.827 milliamps. Now, next one is again checking the second condition for the saturation. For that, we need to use the Kirchhoff's voltage law for the output loop. So I start at VDD and I go all the way to ground. So I say VDD is equal to the voltage across RD plus voltage VDS and the plus voltage across the RS. Now, since these two curves are equal to each other, so ID and IS, I can assume that this is actually just one branch. So I can take then the RD and the RS together and then do times the ID. That is valid because these two curves are exact same. And I can now express the VDS in terms of the other parameters. You see that here 1000 for the RD and the 630 for the RS. And this ID is just calculated here. And now when you do the calculation, you get here 5.243 volts. Is this now valid? Is this now fulfilling the second condition? Let's check that. Well, VGS minus the threshold is here 3.251 minus 1 is 1.251 volts, which is definitely less than this one. So this is also again according to our assumption. So we can say saturation region is valid and our assumption is now by these two checks are correct. All right. Let's now continue with the AC analysis because we have now done the necessary calculations in the DC analysis. To continue, this is now the circuit we will use, which is the small signal model for the circuit here. This part only is the small signal model for the MOSFET. We don't have the channel length modulation. That means we don't have the RO between the drain and the source. We see the VGS and we see here also the voltage controlled current source. So it is a current source, but it's controlled by this voltage source. We also have that the VDDs is shorted because all the DC components are disabled or shorted. In this case, we have here the short, that's for DC voltage sources. So that means R1 is going also to ground and RD also, and all the capacitors are also assumed to be perfectly shorted for this analysis. That means the RS is also shorted, so that means the source node is grounded, which is actually shown here. So R1 and R2 effectively parallel and RD and RL also effectively parallel because this is going to ground and this is also going to ground. So how do we then continue to determine the voltage gain and also the maximum voltage gain? Now let me first designate this node VG, which is the gate node. And I can then say the following: the total voltage gain, AV, is actually a product of two terms. We can write it down in this form, which is convenient. We can say the first term is the gain from the input voltage, VI, to the voltage at the gate node, which is VG. In this case, you can see that this is a voltage divider. We will see that shortly in more detail. The second one is the gain from this gate node all the way to the output. And that is the part where we can use in order to come to the total voltage gain. Now, the A1 is the VG divided by the VI. That's this one, which is an actually voltage divider. Since this circuit part is disconnected from the right side of the circuit, because there's an open circuit here. And we can say VD, which is the drain voltage. Then you can say A2, which is the second part, is VD, that voltage, divided by the VG. And that is the common source amplifier action actually, because this voltage is also the VO. And you look actually at this node to VGS effectively. So we can see that VG is VGS, as shown here, and VD is actually VO. All right, so we have here two fractions we can use in order to come to this voltage gain VO over VI. So let me write it down. So VGS instead of VG over VI is this RG over RG plus R1. What is RG? RG is actually the parallel combination of these two resistors. So we can just combine them together and name it as one resistor. And you can put it here. And the VO is this voltage. Actually, this node is the current flowing through it times the parallel combination of this RD and RL, which is actually shown here. Since it is inverted, because this current is going from this node to ground, while we measure actually from this node to ground, so it's actually inverted. That's why we have this minus GM VGS, which is our current, times the parallel combination of these two resistors. We can now make the ratio. We can say VO over VGS. That's actually shown here. And now we have the ratio we want for this second part, A2. Okay, now we have it, and we can also say that RD parallel to RL is then also written in this form. Now we can say the voltage gain is now the product of the A1 and A2, these two in a product, and that's actually shown here. And now we can also write it down like so. So we have now here the minus GM times the parallel combination of RD and RL times this attenuation factor from this first part A1. Okay, let's now also calculate the required GM, because that's the only unknown here. For that we need to have the DC drain current from the DC analysis, and we can use the formula GM is equal to 2 times the square root of the product of the drain current DC times the Kn given here for the MOSFET. Now let's substitute that, and you get here 12.51 millisiemens. This is a conductance. Okay, let's now substitute that here. So we can do that. Here you see that minus 0.01251 from the GM. This is the 1000 or 1 kilo ohm. This is the 4 kilo ohm divided by the summation. And this is the parallel combination of the RG, which is actually shown here. So 272.7 kilo ohms. And that will result in almost minus 10 as the gain, which is then 20 dB. All right, that was for question A, which is also the maximum gain for this circuit. Okay, continuing now for the lower cutoff frequency. For that we need to go to the small signal circuit for frequency analysis, and that means the 3 capacitors C1, C2 and a CS will then come into picture. You see that actually here. And what we will do now is we will use the short circuit time constant method. So we will consider one capacitor at a time. That is actually the method we are actually talking about. So we consider one capacitor at a time, like in the superposition, and then we will evaluate how we then approximate the lower cutoff frequency later. So contribution by C1 only, that's actually what we want to do. What we do is we disable all the independent sources. That means this will be shorted. And we'll also look between the capacitor C1 what we actually see. So, and all the capacitors will be also disabled. That means these are all shorted. So this VI will be shorted. That's actually shown here. So gone. This is actually just a wire now. CS is a wire and C2 is also a wire. Okay. So we actually consider the C1 as sort of a voltage source, and we assume that is the only active component in the circuit. So we will determine now the impedance seen between the nodes of this capacitor, C1. Now for that we need to use a time constant associated with this capacitor C1, which is given in general form for the RC circuits, like the capacitor itself times the impedance seen by this capacitor, which is now in this case called Z sub C1. Now if I look at this left side is looking to Ri going to ground, and the right side is actually looking to R1 and R2 parallel, again going to ground, which was actually our RG. And that means I have now actually this in series, which is seen by the capacitor C1. So I can write it down in this form. So this one, the summation here, Ri and Rg, is actually this impedance ZC1. So we have everything because the C1 was 1 microfarad, and this is 100 ohms, and this is 272.7 kilo ohms. So together we will end up to 272.8 milliseconds. So we're almost there for this contribution of the C1. So the pole frequency associated with this capacitor C1 is then 1 over this time constant, so 1 over this tau, and that will result in 3.665 radians per second. So almost 3.7 radians, which is a small value, but that's the contribution only because of C1. Well, we can now continue with the other two capacitors. So we will do now for the capacitor C2. So what is now the contribution due to the C2 only? So we again disable all the independent sources, so this is still a short. Now we will short the C1 and the CS. And we will look between the two nodes of the capacitor C2. So CS is gone and C1 is gone. So what do we see? Well, in this case, this is, by the way, short. That means this is a ground. Since this is a short, that means we have here actually 0 volt applied. And if I now do again the voltage divider rule, that means that this voltage node here is also 0. That means I measure here between these two nodes 0 volts. That means 0 volts VGS, meaning GM times 0, meaning this is a current which is of 0 amps. That means this is an open circuit. So that means actually affected the following. So in order to determine again the impedance seen by this capacitor, we don't have this part to the left side, we only have this RD and RL actually. So the time constant associated with this capacitor C2 is just the series combination of the RD and RL. That's shown here. So we can add them up. That's actually this time constant. So 1000 and 4000 from the given. That will result in 5 milliseconds. Alright, now again, the pole frequency associated with this capacitor C2, as we have done it for the C1, that's 1 over the tau. That is now, in this case, 200 radians per second. Okay, next one is about the capacitor CS. So what is the contribution by this capacitor CS only? Again, disabling the input and now the two other capacitors C1 and C2. So those are the two nodes we will use, and C1 and C2 are gone. So how to determine that? Now that is a little bit more work because we need to do it a little bit more carefully. So again, determine the impedance seen by this capacitor CS. So what I do is I will first look at the time constant formula. That's this. But I need this ZCS, which is not just RS, because I see something which is going up there. So I need to do it a little bit carefully. So what I do first is I will remove the CS and I will say this is the impedance I'm looking actually when I look into the source node, and this is the part I need to determine. So that means I can now here, that is one of the options, I can apply here a test voltage, I call it VT, at the source node, and then determine the current because of this test voltage, and then determine from there the impedance using Ohm's law. So in more detail, this is now the voltage I apply, which is our VT, which is our test voltage. And this is the current I actually then will determine, and the ratio of these two, just Ohm's law, will be then this ZCS, which is the impedance seen by this capacitor CS. Okay, this is by the way a generic method also used for the determining the Thevenin resistance in more complicated circuits. So if I now apply here the Kirchhoff's current law at this node S, source node, I will see GM VGS plus this test current will be then equal to this current here, which is then VT over RS. That's shown here. But if I look at this, this is of course the parallel combination of these three resistors. And since this is open, there is no current here. That means this is also, this node, the gate node, is effectively actually grounded. So there's no current actually flowing through these resistors. And since the plus side of this VGS is here and the minus side of this VGS is there, that means the VGS is actually minus the VT, because that's just flipped. You can see that actually here. That's just the flipped polarity. So I can replace this VGS by minus VT, that's shown here, and then replace this to the right side. So I have then collected all the VT terms. Now I see 1 over RS plus GM in the parentheses times VT, that is IT. Well, I'm almost there because I want to have the ratio VT over IT, that is my test voltage over the test current. And that is now shown here. So I do then 1 over that, that's actually shown here. I can now write it down in a little bit more convenient way. Multiply the numerator and denominator by RS. That's shown here. And now I have the expression I actually wanted, which is the ZCS. You can also see that in a little bit different way, because this is the parallel combination of RS and 1 over GM, sort of the two resistors in parallel. This is more convenient and also handy to remember. So this is our impedance for this capacitor CS. So GM was 12.51 millisiemens. We have already determined that. So we can now continue and use the formula to determine now the time constant and also the pole frequency. So this is the time constant, so 10 to the power minus 5, because that was at 10 microfarads. This is 630 ohms for RS, and the other parameters are shown here, so that will result in 0.7093 milliseconds. So the pole frequency associated with the CS, that's shown here, and that will result in this case 1410 radians per second. You can see that actually this is the largest pole frequency looking in this circuit. Okay, let's now bring everything here and then summarize the results. This is now for the C1 contribution, which is almost 3.7 radians. And that was the RG we have used. And this is the pole frequency for due to the C2. That is exactly 200 radians per second. And this is the pole frequency because of CS, which is then 1410 radians per second. This is now the largest one, and it is almost a little bit more than 7 times larger than this pole here. So how do we continue now to determine the lower cutoff frequency? Because we have to do it now more practically. Well, there are some approximation methods depending on the values of these pole frequencies. Now, again, the GM is used here to calculate that pole frequency. Now we see here actually a dominant pole. Why? Because this one is 7 times, so we have kind of a rule of thumb. So if it is 5 times larger than the other poles, we can assume that this is actually dominating. So in this case, I have here a pole which is dominating the other two. So we can consider that this pole will determine the lower cutoff frequency. So I can say the following: the approximate lower cutoff frequency, omega L, is approximately this pole frequency, which is due to the CS only. So I can say 1410 radians per second. If this was, for example, let's say 700 or maybe 600, I cannot say that. This is then too close to this 200. In this case, I am way above that. So that means I can assume that this is a dominant pole. And if I now convert this radians per second into hertz, just divide by 2 pi, I have now here almost 224 hertz. That is my lower cutoff frequency using this method and assuming we have a dominant pole looking at this ratio. Okay, we of course need to check that. So first we start with the DC analysis in the simulation results. So this is the circuit for this, and you see here the values also what we have used. And this is the table from this simulator, and you see here the values which is also calculated in the DC analysis. Let's go here to the VP1, which is this node voltage V1. That was actually in our case VG. So we have determined that as 8.182 volts, which is actually shown here. So that's indeed correct. We also see here the current through the resistor RD. So this is actually between node 2 and node 6. That is 7.827 milliamps, exactly as we have it. So this is indeed correct. So it's all nice. Let's also look at the simulation results for the Bode plot, because there we see the most of the information we want for this maximum gain and also the lower cutoff frequency. Again, our circuit. What do we see now? We have calculated our voltage gain as -10 or in 20 dBs. That is exactly as we have it here also. So this is very nice. You also see here, by the way, that this is a high pass characteristic. So it starts actually very low for the lower frequencies and then comes up and then levels to this maximum voltage gain of 20 dB. We also have the lower cutoff frequency determined or approximated as 224.4 Hertz, and we see here 225.8 Hertz, very close actually. This is actually a very nice result. So we can say our approximation in this case was valid also for this dominant pole approximation. Alright, was our example considering the MOSFET amplifier having these 3 capacitors in this common source amplifier configuration. We have determined using the small signal model and also the DC analysis our voltage gain and the lower cutoff frequency using the short circuit time constant method. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video.